Well, thanks, Yair, and thanks all of you for being here. It's great to be here. I want to encourage you, I'm going to write on the chalkboard, so I encourage you to come up close where you can see and read what I'm writing. I won't be smashing any watermelons, so the front row is safe. So Archimedes lived a long, long time ago. So he died in 212 BC. And we know that exactly because he died in the sack of Syracuse. So he lived in Syracuse in Greece. And when the soldiers came into the city, they knew about him. They knew about him. He was a famous man because he had been defending the city. He learned how to make parabolic reflectors and set the sails of ships on fire. And he learned how to build cranes that could reach down and flip ships upside down. So when people tried to invade the city of Syracuse, they had a lot of trouble just getting on shore. So he defended the city for 35 years, and they came into they eventually breached the walls, and they came into the city, and they found him, and he was drawing diagrams in the sand. And a soldier, a Roman soldier named Marcellus came up to him and demanded to know who he was, and realizing that he was Archimedes, he said, I have to take this person to the general because this is the fierce defender of the city. And Archimedes said, no, step away. Don't disturb my circles. And so Marcellus killed him. So I thought in celebration of Archimedes, we could just fill the whole room with sand and we could draw our mathematics in the sand. But that didn't fly. So we'll do the chalkboard instead. And this is a special year for Archimedes. If he were alive, he would be 2,300 years old this year. Very good. One of the famous stories about Archimedes is him running through the streets of Syracuse yelling "Eureka!" So what had he discovered? So he was in the bath, and he had discovered the law of buoyancy. He realized that as he sank down into the water pushed back up on him. And that's why he felt like he wasn't so heavy when he was deep in the water. And he realized even more. He realized exactly how much the water pushed up on him. The force of the water pushing up on him was equal to the weight of the water that he had displaced. Why was he thinking about this? What was the issue? Why did he care? So he was famous already for being a smart young man. So he had just finished school, and he was known as the smartest kid in Syracuse. And the king had just had a crown built, so a crown made out of gold, and he had handed a chunk of gold to a famous goldsmith and said, build me a nice crown out of this gold. And he got the crown, and it was really beautiful. It was really nice. But he just had this sneaking suspicion that something wasn't quite right. It just didn't feel right to him. So the king thought that the goldsmith had mixed something in with the gold. Maybe silver. If you mix a little silver in with gold, it's kind of hard to tell the difference. And then the goldsmith could have kept the rest of the gold for himself, and he'd be a wealthy man. So the king wanted to know, how can I figure out whether the crown is really made out of gold without destroying the crown? And there's a lot of valuable work has gone into making this crown beautiful, and how will I tell? So this is what Archimedes was thinking about. So let's go ahead and do this computation for ourselves. How are we going to tell whether a crown is made out of gold or gold mixed with silver? And the key thing that they all knew at this time was that gold is denser than silver. So the same volume of gold weighs more than the same volume of silver. So any guesses? How would you tell?
They would put like a crown that they had, a crown made of full gold in the water and see which was closer to floating.
Great. Okay, so you could make a gold crown that you knew was pure gold to compare it with, and put them in water. And then what are you going to do once they're in water?
Once they're in water, you observe it, and how, like, if it's bobbing up or just sinking.
Okay, so the question is, maybe one of them floats and one of them doesn't, and if one of them floats, then that's definitely going to be the fake crown. That's a good idea. Unfortunately, silver and gold both sink. They're both much heavier than water. So even if it were all silver, it would still sink to the bottom. But here's what a lot of people think Archimedes might have done. They think he might have put them in water and then see how much the water rises. Right? So if silver is less dense than gold, then equal weights of silver and gold, the silver will have more volume, and the water will rise more. So let's do this computation. So say you had a crown made out of gold, and we actually have crowns made out of gold from around this time, and they weigh between 700 grams and a kilo. So just to keep our numbers round, let's pretend it's 1 kilogram, 1,000 grams. That's how much the crown weighs. And I can tell you that gold is about 19.3 grams per cubic centimeter. So water is 1 gram per cubic centimeter. So gold weighs almost 20 times as much per volume as water. So then we should say, well, how much gold is there? So if we have 1,000 grams of gold and it's 19.3 grams per cubic centimeter, we want to know how many cubic centimeters of gold do we have. So we divide, and you'll find that you have about 51.8 cubic centimeters of gold. So that's our crown. So that's what a true crown, that's how much gold there would be in the true crown. Now what if it was 30% silver? So if we had just 700 grams of gold, and we had 300 grams of silver. So the gold is still 19.3 grams per centimeter cubed, but silver is much lighter. It's about half as dense. So silver is about 10.9 grams per cubic centimeter. So if you go ahead and divide 700 by 19.3, you have about 36.3 cubic centimeters of gold. And you have 300 divided by 10.9, so, 10.5. And so this is about 28 cubic centimeters of silver. And so you add them up, and you have here 64 cubic centimeters of metal in this crown that's 70% gold and 30% silver. So the difference is about 13 cubic centimeters. So that's, well, that's just what it is. So now, say we're going to take these two crowns and put them in water. So how big a tub of water do we need? How big is a crown? 3 feet across? Too big. 1 inch across? Too small. So what would you say?
About a foot.
About a foot. Okay, good. So let's say about a foot across. So if it's about a foot across, how many centimeters in a foot? 30. Okay, good. So we have about 30 centimeters across. So the radius is going to be about 15 centimeters. So here's our pool of water. So our radius is 15 centimeters. And so we want to compute, so we have our tub of water. So 15 squared is 225 times pi. So pi r squared is the area of this tub. So pi r squared. So 3.14 times 225, that's about roughly 800 square centimeters. So if we have 13 extra cubic centimeters, so we put our crown in, and we have, so if we put in 52 cubic centimeters of gold, how much is this water going to rise? So 50 cubic centimeters. So this is about 800 centimeters squared times how many centimeters? About a 16th. 16 times 50 is about 100. So it's going to go up about a 16th of a centimeter. That's not so much. What about for the fake crown? So when we put the fake crown in, so now we have to ask ourselves, well, 64 centimeters cubed, so this is about 800 centimeters squared times how much? So it looks like maybe 8 over 100. So what's 8 over 100? That's like 2 over 25. Did I do the math wrong?
No. Your math about right. It's just a little bit thick. We find this is actually a small first.
These two numbers are kind of small, right?
Yeah, but we find it's definitely too small.
Okay, so the difference between these is going to be too small to tell. Yes?
There has to be room for the king's head, doesn't there, in the middle of the crown?
There does.
So you don't have to use this nice big pool. You could exclude part of the center.
Oh, I see. So good. So we could try to exclude part of the center and make a ring-shaped tub to put them in. Good. So there might be some way to adjust this to make it work. But I'm going to tell you here and now, this isn't what Archimedes did. There's no way. You need to have a whole nother kilo of gold on hand to make this work. Right? This gold is too valuable. You don't have an extra crown to compare. This crown is something precious. You can't just make another one to check against the one you have. So what was Archimedes doing in the tub? So Archimedes understood buoyancy, and he understood one other thing. He understood the principle of the lever. So what's the principle of the lever? So if you have a balance, and you hang something on the balance at some distance, d, and you have some mass, m, then when this hangs down, it exerts, it exerts a force, it exerts a moment about the fulcrum. And the moment is equal to the mass times the distance. And so if we have two weights hung at different distances, so if we have a big mass, we should hang it at a small distance. And these are going to be in balance if the two masses times the distances are the same. So if little m times big D is equal to big M times little d, that's a balance. So what if Archimedes only had a small chunk of gold? Say he had 100 grams of gold. Yes? Yeah, right? So if he has just 100 grams of gold, that's his 10th as much gold as was supposed to be in the crown, but he could hang it 10 times as far away. So let's make the type of balance that Archimedes would make. So here he has a little lump of gold, maybe 100 grams, and he's going to hang it far away from the center. And then close to the center, he's going to hang the crown. And now it's in balance. So now what? So this is the principle of the lever, but his big discovery that moment, the reason why he shouted Eureka was because he had discovered buoyancy. So what would happen if both the crown and the nugget were made of pure gold, and they were balanced like this, and we took the whole lever and put it in the bathtub? So there's your thought experiment. What happens if you take this whole thing and put it in the bathtub? What would happen here if this was 100 grams of styrofoam on one end, and you have the crown? Would it still be balanced when it's hanging in the air? Yeah, right? It's just the mass. How much mass is there? 100 grams of styrofoam weighs just as much as 100 grams of gold. It's just a lot bigger. So now when you put that in the water, what's going to happen? Yes?
The crown will sink quicker than the piece of gold.
Yeah, it's not going to be in balance anymore. The crown's going to sink, and the styrofoam would go way up. Yeah, because the styrofoam wants to float. So if this is balanced, and they're made out of different materials, then it will fall out of balance once it goes into the water. And the less dense one is going to want to rise. So this was how Archimedes tested the crown. So he took a lump of 100 grams of gold and he hung it on the lever 10 times as far away from the crown. And unfortunately for the crown maker, this arm sunk and the crown went up. The crown wasn't made of gold. So crown maker died. Archimedes died too eventually, so it's no laughing matter. Okay. So that's what Archimedes did with levers and buoyancy. So this is one half of the method of Archimedes. So the key to what Archimedes was doing was that he was thinking in terms of physics and he was thinking in terms of levers. So for a long, long time, there was a stone just outside of Syracuse that had this inscribed on it. So it was a half of a square, so a rectangle that was twice as wide as it is tall, and it had inside of it a triangle, and it had inside of it a half of a circle. So this was what Archimedes asked to have inscribed on his tombstone. This was his proudest mathematical achievement, was to understand this picture, and not this picture in the plane. So before Archimedes, there was Euclid, and Euclid was very good at plane geometry. He knew how to compute areas of shapes in the plane. But that's two-dimensional mathematics. And Archimedes wanted to take that a step further, and he said, what if you take these three figures, a triangle, a half circle, and a rectangle, and spin them around? So spin them around the vertical line, and what do you get? So if you spin a rectangle, you get a cylinder. If you spin the triangle, you get a cone. And if you spin half a circle, you get half of a sphere. And one of Archimedes' great pure mathematical accomplishments was to understand the volume of these three shapes, how their volumes relate to one another. So think for a moment. So the volume of the cone, is it more or less than the cylinder?
Less.
Less? Good. Is it more or less than the hemisphere?
Less.
Less, because it fits inside. Good. Roughly how much of the cylinder is filled up by the cone? 3/4? No. How much?
Perhaps 5/8.
5/8? Okay. So 5/8 for the cone or for the hemisphere?
For the
For the cone, okay. And for the hemisphere?
since it's like rough, like it's inside of it, I think roughly 6, maybe 6 or yeah, 6/8.
Okay. So maybe 5/8 for the cone, maybe 6/8 for the... Could there be a pi involved? Right, when you think about the areas, right, how are the areas related? How much of the area is the triangle inside the rectangle? Half. Right? Good. So half. And now as we spin it around, how much of the area of the triangle is close to the center? Is more of the triangle close to the center, or is more of the triangle far from the center?
With the triangle far from the center.
Most of the triangle is far from the center? So if I make a little strip here, and if I make a little strip here, which strip is bigger?
The strip that's closer.
The strip that's closer to the center. And then when I spin them around, which one is going to make a bigger piece when it spins around? The small one, right, is going to spin around further. It's going to make a bigger chunk in the cone. Good. Okay. So do you think the triangle, when you spin it around and make a cone, is it going to be half the volume, more than half the volume, or less than half? Let's draw another picture. So we take our rectangle. Let's say we choose half of the rectangle in a different way. So here's the center. Let's say we take this half, the half I shaded in, and spin that around. After you spin it around, is the volume half, more than half, or less than half? Yes? Half?
On the right and left side, there's it's about the, okay, so in the middle, there's like a line of symmetry.
Mm-hmm.
That line is about 1/4 of this part. And for the right and left portion is about 1/4 each.
Mm-hmm.
I'd say it's about half. If you add them together.
So you're right, it's half in this picture. Let's look at it from above. So let's take it, let's fly up above this picture, and let's look down on the cylinder from above. So now we shade in the half that's on the outside. We shade in, so from the center we go halfway out, and then we shade in the rest of the way. And now if you take a wedge, which part of the wedge is bigger?
The one that's shaded.
The one that's shaded, right? The outer part. The wedge is getting wider as you go out. Do you see what's happening as you spin around? That even though these two areas are equal, the inner area and the outer area, the outer area is sweeping out a bigger volume as it rotates around. So here, if we spin this around, the outer part is going to be more than half, even though it's only half the area. Okay, good. So this triangle, more of its area is close to the center, and less of the area is far from the center. And so when you spin it around, even though it's half the area, it's going to end up being less than half the volume. So do you know the volume of a cylinder? Do you know a formula for the volume of a cylinder?
Pi r squared times the height.
Good. Okay, so pi r squared, which is the area of the base, times the height. Very good. And the cone?
Is it a third of that?
Exactly. It's a third. So a cone is a third the area of the base times the height. And this was something that Euclid knew. So this was known before Archimedes, and there's a really nice way of seeing it. So you imagine taking your circle and you cut it up into little triangles. And so then you take your cone, and your cone gets cut up into triangular cones. And you can take this triangular cone and put it inside a prism. So a prism is just a triangle moved straight upwards. And so its volume is the area of the base times the height. And then you can cut this triangular prism into 3 pieces, each of which has the same volume. And they fill up the whole prism. So Euclid knew this. And so then you put them all together, and you get that the cone is a third the area of the base times the height. So now let's think again about the hemisphere. So what portion of the area of the rectangle is filled up by the area of half a circle? So let's say this is 1 unit high, so the radius is 1. What's the area of the rectangle? Anyone? I hear 2. I hear 2 somewhere. So 2, yes. Don't be shy. Okay. So the rectangle is 2. And what's the area of the hemisphere? The hemicircle, half a circle. Pi over 2, right? So the area of a circle is pi r squared, and this is the radius is 1, so the area of the full circle is pi. So the half circle has area pi over 2. So the ratio is pi over 2 is pi over 4. So a little more than 3/4. Now when you spin them around, is it going to be more or less than 3/4? Okay, I see someone thumbs down. It's going to be less, right? Just like the cone, the circle is taller near the middle and shorter near the edge. So it's going to be less than 3/4. Good. So before Archimedes, no one knew what the volume would be. And it's a hard problem. So it's a calculus problem to compute volumes. This is what calculus is very good at. And someday you will learn calculus. And I gave this problem to my calculus students in the fall. So Yale sophomores and juniors. And about half of them could do the integral. It's not an easy integral. So even 2,300 years later, with all the math we've learned, it's not such an easy computation to do. But Archimedes had a clever way of doing this. So he said, well, if I can't compute the volume of a sphere, maybe I can compute something else. And his something else, so another eureka moment for him, was he decided that if he hung the sphere on a balance, that he could compute the moment of the sphere about the fulcrum. So this is some four-dimensional quantity. It's a volume times a distance. The volume is three-dimensional. The distance is one-dimensional. So there was some three-dimensional integral that he could not do, and he replaced it with a four-dimensional integral that he knew how to do. And so he said, well, so he took a sphere of radius r, and it turns out that he wanted to hang it at distance 2r, so twice the radius from the fulcrum. This is just what he decided to do. And what he said was, well, as I go, I can think of my sphere as being made out of slices. And as I take slices going down the sphere, at least at the beginning, these slices are getting bigger. And so the moment of each slice about the fulcrum is going up. And he said, well, on the other side, let me put something else. And the something else that he chose was a cylinder. And so he put a cylinder on the other side. And he decided, instead of slicing the cylinder from top to bottom, he sliced the cylinder from left to right. And so now all the slices have the same size, but as you move from left to right, they're further from the fulcrum. So they exert a greater moment about the fulcrum. And he might have even built a balance like this. And what you'll find is that it's not, so in the cylinder that he chose, had radius 2r and length 2r. And it's not in balance. And you can see that it's not going to be in balance. As you come down, the slices start getting smaller here. What Archimedes realized was that the difference between these two was exactly a cone. And so when he drew this picture, what he was expressing was that he felt he fully understood the relationship between a cone, a hemisphere, and a cylinder. So this cone has radius 2r and height 2r, and Archimedes just tells us that these are in balance. Yes?
You said he understood that the difference was the cone.
Yes.
How did he understand that?
He was a genius of the greatest order. There's some things that one can't explain. He lived for 75 years. He was a truly brilliant man. And he thought and thought and thought all the time. And this was something that in the course of his research, he saw and understood. So he didn't have algebra. So he wasn't able to write things out in equations the way that we can. But we can go ahead and use our equations and understand what he saw. So let's do that. So as we go slicing these three objects, we're going to slice the cylinder from left to right and the sphere and the cone from top to bottom. And so let's take our slice at distance x. So at time x, we take this slice. And the area of this slice, so a circle with radius 2r, the area is going to be pi times the radius squared. So pi times 2r squared. So on the cylinder side, we have pi times 2r squared, and times the distance. And the distance now is x. That's how far this slice is from the fulcrum of the. Now on this side, we're going to have to think for a moment. Let's do the cone first, because the cone is easier. So the cone has height 2r, and at the bottom it has radius 2r. And the radius is increasing steadily from 0 to 2r. So when we do the slice at height x, the radius will be x. Great. So we have pi x squared times what? Times the distance, 2r. So that doesn't look anything like what's over here. Right? Here we have an r squared times an x, and here we have an x squared times an r. This looks like trouble. But we still have the sphere. Yes?
When you wrote pi x squared times 2r, weren't you using something more that all of each of those disks is 2r away from the fulcrum?
Ah, oh, good. Good question. That's right. Not the whole disk is at distance 2r from the fulcrum, but Archimedes understood that any mass behaves like a point mass at its center of gravity. And so this disk has a symmetry, and so the center of the disk is, the whole disk will behave like its entire mass concentrated at its center of gravity. Yeah. Yeah. So here, now we have to do something a little bit trickier. We need to compute what's the area of this slice of the sphere. So we can go back to what we know about algebra. So we have a circle, and we're going to put the circle at the point r0 in the plane. So that as we start at time 0, we have a slice. And so when we take the slice at distance x, we want to know how high is this slice. So the equation for this circle, so you might know, is, so if you have a circle centered at 0, 0, it's x squared plus y squared equals r squared. But here we've moved everything to the right r. So instead of x, it's x minus r. So x minus r squared plus y squared is equal to r squared. And we can expand this out. So it's x squared minus 2xr plus r squared plus y squared is equal to r squared. And the r squareds cancel. So those go away. And you have y squared equals 2xr minus x squared. And so this y, so this is what we're interested in. Y is the height of that slice there, which is the radius of our circle here. So when we have pi times y squared, that's pi times 2xr minus x squared. And again, so the center of this disk is at distance 2r. So now we add up what's happening on the left. So we have 4 pi x r squared minus 2 pi x squared r plus 2 pi x squared r. So these cancel, and this is what we're left with. 4 pi xr squared, which is exactly what we have on the right. So this is what Archimedes saw. He saw that these were in balance. And so now that he knows that they're in balance, he can go ahead and solve for the volume of a sphere. So he knows the volume of a cylinder, and he knows that its center of mass will be at distance r from the fulcrum. And he knows the volume of the cone. Do you see that? That now we know enough to solve for the volume of a sphere. So on the right-hand side, the volume of the cylinder is the area of the base times the height. The height is 2r, and the area of the base is pi times the radius squared. So we have the height, which is 2r, times the area of the base, which is pi times 2r squared. Yes, question?
Could I just ask you to show each, just the first slice again of each that you're adding up as before you proceed along in x? The expressions that you wrote there for the slice on the top of the sphere.
The top of the sphere, so this distance is x.
And then the top of the cone.
Distance x.
and the left side of the cylinder.
Yes.
And they're all the same as you go through each object.
Yes. And there's some leap of faith that if each of these slices is balanced, then the whole object should be balanced. Archimedes did not accept this as a proof. Yeah, so there's a wonderful story behind this. So Archimedes did not accept this as a proof. He used this to figure out what the volume of the sphere was. And then once he knew the answer, he found another way of proving that it was correct. And then he hid this, and he didn't tell anyone how he had actually done it. And shortly before he died, he wrote it down. So in between times, he was writing letters to his friends in other cities, and he was taunting them. So he was saying, I know the volume of a sphere. Can you guess what it is? And then when they didn't respond after a few years, he would tell them what the volume was. And then he would say, can you guess how I got this? And they still didn't respond. So eventually he wrote it down. And we lost it. We lost it. So it was, and then we found it again. So the one copy that we have where Archimedes explains this picture was written in year 987. So it was written down in Byzantium in 987, in Greek. It was copied down. And paper at that time was extremely valuable. And over the years, what Archimedes had said seemed less and less important. And other things became more important. And so they washed the paper so they could reuse it. So they went ahead and washed off everything that was written about this picture. And they wrote a religious text on top of it. And so that was done in year 1220, thereabouts. And in 1840, a Bible scholar, a biblical scholar, traveled to what was then Constantinople, now Istanbul, and found this text. And read it and thought it was interesting. So he was studying the religious content of the text. And he brought a page home to Cambridge. And a Danish language scholar saw this page. He was a philologist, so he was interested in the historical use of language. And he saw that there was this mathematical writing underneath. And he recognized it as Archimedes. And so he traveled to Constantinople to see the rest of this text. And his name was Heiberg. And so in 1906, he took photographs of the entire text, page by page. He took photographs, and he brought them back to Denmark, and he wrote about them. And so over the next 10 years, he published his transcriptions of what was written in these lost texts of Archimedes. And then we lost it again. It disappeared from 1920 until 1998. So many of you were not alive then. But I remember when this book came on auction. It was in the New York Times that they had rediscovered this book. It had been sitting in someone's basement in France for 70-some years. It had been defaced, so someone had added counterfeit Byzantine paintings to a few pages, trying to increase the value of this manuscript. But it was found, and now we have all this technology. So infrared reflectography and X-rays, and they've studied every page of this. And we now know an awful lot about what was washed away. So we can still read the traces. And that's the only way we know that Archimedes figured out that these solids balance. So let's solve the equation. So what is the volume of a sphere? On the right-hand side, so let's expand this out. So we have, so this is the area of the base, this is the height, and the distance of the center of gravity from the fulcrum is r. So when we expand this out, we have a 2 squared times a 2, so we have an 8 pi times r to the 4th. So now let's do the cylinder, or let's do the cone. So the cone is at distance 2r from the center, and its volume is 1/3 the area of the base times the height. So 2r times 1/3. Now the area of the base is again pi times 2r squared. And the height is again 2r. So if we multiply it out, we have 2 squared is 4, times 2 is 8, times 2 is 16, divided by 3. So we have 16 over 3 pi times r to the 4th. So 8 pi r to the 4 times minus 16/3 pi r to the 4 is the volume of the sphere times 2r. So the volume times 2r is equal to, now what's 8 minus 16 over 3? We'll put everything over a common denominator. So 24 over 3 minus 16 over 3 is 8 over 3. So this is 8/3 pi r to the 4th. And now we can cancel an r and make this an r cubed. And we can cancel a 2 and get a 4. So the volume is 4/3 pi r cubed. Now if you cut the sphere in half, the volume of half the sphere is 2/3 pi r cubed. So here, in this picture, the cone is 1/3 the volume of the cylinder. The hemisphere is 2/3. So it's a very simple ratio. It's just 1 to 2 to 3. This is what Archimedes discovered with his method. And like, yes,
You did this using algebra,
right,
but he didn't use algebra.
no,
He just was able to do it because he was a genius.
yes.
You have to be a genius throughout the
Okay, so one thing that any mathematician worth his salt will tell you is when you have a new method, you milk it for all it's worth. Okay, so Archimedes had a new way of computing things that nobody else knew. And he used this to compute many, many things. So he said, well, once we've taken a triangle and half a circle and we can spin those around and we can compute their volumes, what about a parabola? What if we take the parabola and we spin it around and then slice it? So it looks like that. He can compute that, the volume of that. And if you're going to hang that on a lever, you're going to want to know where the center of gravity is. Right? So where's the center of gravity? He'll tell you. He'll tell you where's the center of gravity of a hemisphere. Right? It's somewhere on this line, but where? How does it compare to the center of gravity of a cone? Okay, so center of gravity of a cone, if you play with it, you'll figure out the center of gravity of a cone is 1/4 of the way up. Now a hemisphere is more top-heavy than a cone, so it should be higher up. So a good thing to play with. Where is the center of gravity of a hemisphere? So Archimedes knew. And the final thing that he computed by his method was he looked inside a cube and he inscribed 2 cylinders going in perpendicular directions, and he intersected them. So take the intersection of these 2 cylinders, and you can think about what that looks like. 2 cylinders inside a cone and intersect them. If you look down from the top, you just see you see a square. Right, so do you see that? That at this section, halfway up, you get the whole square. And as you come down from the top, well, you should think about what you get as you come down. So what's the volume? And the reason why Archimedes loved this particular computation was all the other volumes of round objects that he knew. So a cone is somehow round, a cylinder is round, a sphere is round, this paraboloid is round, and all of their volumes involve pi. And he knew that pi was irrational. So the volume of this intersection of two cylinders, it's somehow a round shape, but its volume is rational. So if you do this inside the unit cube, you get a rational volume. So I leave that as a challenge for you to think about. What is the volume of the intersection of two cylinders in a cube?